Okay, let's get started. I hope you guys had a good mini break. Today we're gonna learn more about FSM, finite state machines. Okay, so last time we talked about how to model FSM using these abstract diagrams. So today we're gonna look at how we start from the abstract diagram and then create the actual circuits. Okay. So before that, as usual, some announcements. Homework 3 is due tomorrow. For this one, we plan to release the solutions right away on Saturday so that you guys can read it to prepare for your prelim. So one thing to remember, so in case you want to request slip days for this homework, right, you will not, so let's say you do not submit before Saturday. So that means you will not be able to see the solution. So we're gonna release the solution on CMS. Okay, so be careful. Okay? But the moment you submit, you should be able to see the solution. Okay, and also we plan to release the grades and also solutions for homework 2, most likely today. And also to help you guys better prepare for the prelim, we're gonna cancel the lab hours on Monday. Okay, on Monday only, right? Not Wednesday. We have already extended the deadline for pre-lab 3B, right, until next Friday. Hopefully this will give you guys more slack. In case you're already done with pre-lab 3B and also some of the, it should be 2. Okay, yeah, the typo. Press 2B. I'm gonna correct this. Right, in case you're already done with certain part of the lab, you want to check it off, right? You can go to the TA office hours. Okay, and a little bit more about the prelim. Right, I think last time I already mentioned that it's going to be open book, right? Open notes. Also told you guys to arrive at least 5 minutes earlier. One thing is we're going to create a new Zoom link. Right, this is the short URL. Okay, so we will create multiple breakout rooms. So when you sign in, you're supposed to be automatically assigned to a breakout room. Okay, again, make sure that you turn on your camera right away. Right, so the TA will check. So each TA will have a list of the students who are supposed to be in certain breakout room. The TA will check, make sure that the student all arrive and all students have turned on the camera. And we are going to be releasing the exam through item pool. Okay, so this is important, right? Since we have already tested, right? We also thought about Google Drive, but actually for some students in some country, they may not have good access to Google Drive and they have to use VPN. So that's the reason that we are going to be using item pool. But one thing is, so we'll only release the questions on item pool. We're not going to ask you to submit answers because in some cases we will ask you to draw diagrams. We will also ask you to derive some of the use theorems, right? To simplify, either simplify or prove certain property of the Boolean algebra. So that's where we will ask you to write on the blank sheets. Okay. Right. Yeah. So yes, same thing for the alternative prelim slot. Okay. I think we have the TA have already contacted you guys, right? If not, can you make sure that you email us again? I already asked Lisa to contact everyone who have to be taking an alternative prelim, alternative slot. Okay. So where am I? Right. So I was talking about item pool. Right. So we will give you the link 3 minutes before the exam. Right. So that's gonna be basically 12:57 around that time. We're gonna give you the exam. Good question. So Steven's asking whether you can use a tablet if you have a pen and if you feel that's more convenient. Yes, but as long as you're not typing, okay? As long as you're not using the tablet to type and communicate, so that's not allowed. Right? As long as you're not doing that, that's fine. Okay. So we're going to be posting a more detailed exam protocol on Piazza, hopefully either later today or tomorrow. We also include a complete Zoom link, right? But maybe before that, so let me send you guys the link. Let's do a quick test. Okay. Right, so Arush is asking, so how do you submit answers, right? So over here, you're supposed to write it on the blank sheet, and then we will give you 5 extra minutes to scan the answer and upload to CMS. We have already created a CMS assignment for prelim, not item pool. Submit everything to CMS. Okay, so let's do a quick test. So can you guys go to this link? I created a mock-up test. Make sure that you can make sure that you can access it. Are you guys able to access it? Cool. All right. Okay, so basically, the item pool will ask you to enter your net ID, right? So please do so, so that we know who is able to access and view the exam, right? But later on your white sheets, please also make sure that you write down your name and net ID. Okay, so before scanning in, make sure to double check. So supposedly you'll be seeing this page, right? So this is a mock-up test. I actually copied some questions from the old prelim, right? Although I did not copy the Q1, right? I copied some random questions from there. So one thing I want you guys to pay attention to is, so see here, we are only gonna allow you to, right? So to view the exam through item pool. We don't provide any like chat boxes or blank fields for you to fill in, right? So that means basically there's no way to type in your answer, right? This is by design. This is intentional. But when you click, right? So when you click next, so this is one little annoying thing about item pool, right? So even though we are not really asking you to enter anything, the website may still ask you about this question, right? To skip, that will be marked incorrect. Just click skip. Okay, this is totally fine, right? We are not going to be grading on item pool, so this is totally fine. So this will allow you to view the next question, right? Again, when you click next, so same thing, skip. So good thing is, you only need to do this once, right? So you can go back and forth, right? You can click next, previous, right? Next, right? And you should be able to view the whole exam, right? By just clicking these 2 buttons. Don't worry about these things. Don't worry about like 0 out of 10 points. Okay, don't worry about this, right? So we're going to be grading the answers that you submit to CMS. Okay. Any questions? I think there are a lot of questions. A lot of them. Yes. So again, this is not convenient for me to check. Right. So it looks like most of you can access. Right. So if you cannot access this link, can you send me an email, or can you send an email to staff, ECE2300 staff? Right. Okay, so another thing I want to point out is I have also, in case you guys haven't noticed, right? I've also posted the links to all the previous quizzes on this page. Okay. So for example, over here, if you click this one, okay, you will see the quiz from last time, right? This is about FSM, right? If you want to do practice again, right, you can start it. Right, this is my net ID, right? This is a question that we did last time, right? I asked you guys to enter the output sequence given this input sequence. So this is actually a pattern detector, right? So this is a Mealy machine, so we are detecting 0, 1, right? Anytime you see 0, 1, so we are supposed to output the 1, right? So the output sequence will most likely look something like this, right? So for these release quizzes, so you can actually check your answer. Okay, so the solution is released on item pool, right? You can actually check it. All right, so this is about item pool. Let me go back to my screen, the other screen. Okay, so yeah, on the screen, I can actually see some of the answers, some of the comments, and also it's good that many of these questions are already answered. Okay, once again, so if you are not able to access this item pool link, let me know ASAP. Okay, either directly email me or ECE2300 staff. Any more questions about the interface of the exam and how you do it? No? Okay, good. All right, so also, if you have seen Lisa's post right on Piazza, we have scheduled another TA-led review session today, right? This is going to happen tonight at 7 p.m. Eastern. Please go to the lab Zoom room. We are going to record it. Okay. Right, so yes, Hogan, we are going to be recording it. Okay. Any more questions about Brim? Like I mentioned, we are going to be using, right? This is important. So please do not come to this room, the lecture room. So please go to this exam room. We will post a complete Zoom link soon on Piazza. Alma is asking, should we do the practice prelim before the review or we'll go over it? It's up to you. I don't think we will go over the practice prelim since we have already released the solutions. But I can double check with Lisa. So if you have questions about practice prelim, right, so feel free to bring it up right, during the review session. Okay. All right. Okay, it looks like there are more questions about prelim, which is good. So do we have to log into item pool for the prelim? As long as you can see the test, that's fine. It may ask you, there might be a prompt, right? For to enter your name, just enter net ID. Okay, so this will be useful for us anyway. So we actually know who accessed the exam. But the important thing is that if you're already logged in, that's fine, right? You're able to see the test. Okay, you don't have to log in again. Also, do the notes we use during exam have to be printed, or is it okay to have it on our device? So, Lauren, you're talking about the what kind of notes are you talking about? You don't basically the ones that are not related, not directly related to the answer. For those, you don't have to scan them in. You can just leave them on the device.
Okay, I was just asking because you mentioned like typing during the exam is not good, but if like we had like a PDF or something,
You mean
that would be okay.
you're gonna be using a smart pen to write on tablet?
Like for because like the exam is open note, would it be okay to have like a PDF of notes?
Yeah, you can open you can open the notes on your computer.
Okay, thank you.
Or the ebook. Right, that's totally fine. Right, as long as you just need to click, right? You don't have to type that much. Linka is asking, right? So this one's going to cover lecture 1 through 7, right? So that's a coverage of the first prelim. And you should also review the first 3 homework up to after lecture 7, where we cover Verilog. Okay. And also remember that there are actually a few slides, right, in lecture 8 about Verilog. Those might be useful as well. But most of those are already covered in lecture 7. Oh, one more thing about Verilog. Okay, I'm not going to be asking you guys to write down Verilog code. Okay, so you only need to be able to read some Verilog code. That's good enough, right? Okay, so this is about prelim. Somehow my laser pointer is not working. Good. All right, so let's come back to FSM. Last time we talked about different kind of state machines, right? FSM is a finite state machine, right? We have finite number of states, we have finite number of transitions, we have finite number of inputs and outputs. We talk about FSM being the abstract model, right, to describe any kind of sequential logic, right? So this is one way to describe FSM. This is more like a hardware-oriented diagram, right? Last time we actually talked about two kind of FSMs, right? So can you guys tell me like what is this? What is this? Is this a Moore machine or this is a Mealy machine? This is Moore, right? Very good, right? So the key thing is to distinguish between Moore and Mealy, the key thing is to look at the output, right? So look at the output side. If the output only depends on the current states, right, then we have Moore machine. If the output actually depends on both the current state, the state, and the inputs, then we have Mealy machine. Okay. And last time we did talk about, right? So we have this notion of current state, which is basically the output side of the flip-flops. We are using the flip-flops to store the states, right? And incoming, right? So you look at the incoming edges to the flip-flop, basically input side of flip-flop, we call them next state. So in this lecture, so we're going to name the current state as S, has been state, okay? And we will name the next state as S star. Okay, so this is going to be our notation for this lecture. All right, so again, this is a Moore machine, right? Since output depends only on the current state values. And we also talk about Mealy machine, right? So with Mealy, output depends on both inputs and the current state values. Okay. So last time we also went through, I think we went over some problems, right? We look at if we define a problem, right? First, given the problem statement, right? So how do we define the states? How do you identify the states, and then create a state transition diagram, right? So this is what we talked about last time, the first two steps. And today, let's look at how do we, right? So actually derive the complete circuit out of the state diagram. So we have 3 more steps to go. First, we need to determine, right? So how many flip-flops do we need, right? So basically, how much storage do we need? And then we also want to implement the combinational logic, right? So we do need to although so FSM is describing sequential logic, we do need to create combinational logic for computing the outputs, right? And the next state. We'll also run some Verilog code to test our circuit. Okay? So hopefully, some of the things that I'm going to cover today will also be a good review, right? For some of the things that the prelim one will test. Okay. So there are more questions about prelim. Right? Max is asking, does it include lecture 8? So again, if you're good with all the materials that covered by 1 through 7, that's good enough. But lecture 8 does have some additional, right? So clarifications on the non-blocking and blocking assignment for Verilog. So those might be useful as well. Okay. All right. So let's do a quick recap, right? And this is a problem that we look at the end of the last lecture. We were trying to build the pattern detector. So we have 1 bit input, right? So we have 1 bit input, 1 bit output. So we actually build FSM to detect this 111, right? So we try to detect this pattern. Then we do allow these overlapping patterns, right, to be detected. So meaning that, right, in this case, in this case, right? So we're going to generate 1 here, right? Since we have 3 ones, then we're going to generate another 1 here. Okay. And the clock, right? So one important thing is, so in many cases, actually just assume that the clock is there, right? We don't explicitly draw it. The clock input is always there. All right, so these are the diagrams that I drew on my tablet last time. Right. I think all of you agree that those FSMs look good, right? And these are the diagrams in right, in a prettier form, right? So we have drawn both Moore machine, the Moore diagram, and also the medium diagram. So for the Moore diagram, we have 4 states, right? So in case you need a refresher of this Moore diagram, so make sure that you put the output right inside the state bubble. Okay. Each state bubble needs to have an output, and these are the inputs, right? So we put the inputs on this transition arcs. For Mealy, the outputs are not inside the state bubble, right? Because the output depends on both input and the state. So that's where we actually put output on the transition arcs. So these are the key differences. So again, this is actually doing 1-1-1 detection, right? So if you look at any given state, right? So let's say you look at got1, right? You know, if we have a 1, so we go to got1-1, right? We get sorry, it should be, let me start with the init. So before I in order not to confuse you, okay? So we start with the init state, right? So we get 1, right? We go to got1, right? If we get another 1, right? So that's where we go to got1-1, right? And then if we get 1 more, so that's where we output 1. So and if we get 0, then we come back, right? Otherwise, we keep outputting once. These are the state diagrams. So now let's look at how do we actually create the circuits. So like I mentioned, so we're going to be using S* to indicate next state, okay? And we're going to be using S to indicate current states. Okay. So actually, our strategy here is actually very similar to, although we're dealing with the sequential logic, right? So our strategy here is going to be very similar to the combination logic. So given combination logic, so what do we do? So given a problem, I think you guys have done many exercises, right? For creating and minimizing combination logic, what do we do? What are the things that we do first? Given a problem, given problem definition, what do we do first? What is the first thing that you guys construct? Very good, right? Right. Many of you are saying truth table, right? Very good. We need to create a truth table. Actually, same thing here. So for sequential logic, we also need to create a truth table, but this one has a slightly longer name. It's called transition output table. Really, just a fancy thing, but what it's doing is just a truth table. Okay. So how does this truth table look like? Let's take a look. So given this Moore diagram, again, this is a 1-1-1 pattern detector. So we want to create a table, right? So to capture, so basically we want to know the correspondence between the output and the input, right? So what are the outputs in this truth table? Now, of course, we have the regular outputs, right, from the circuit. Any other outputs that we need to care for? Next state, right? Very good. Okay, so this is something that it's important to keep in mind, right? For sequential logic, for FSM, we actually need to build sort of 2 combination logic clouds. So for one for computing the actual outputs, the other one for computing the next state. Right? Here's the truth table for Moore diagram. Over here we have the inputs, right? So these are where we put the inputs. So the inputs and the current state. Okay, over here, they also serve as inputs. Okay. And we have the regular outputs, and we need to compute S star, which is next state. So in this case, I directly just put in the names of the state, right? So hopefully this table is somewhat intuitive to you guys, right? We have 4 states, right? We have 4 states for over here. And since we have a more diagram, we have more machine, okay, given input state, given current state, not input state. So we have the corresponding output, right? So in it, we output 0, right? In GAL1, we output 0, right? Etc. So this is how we capture the, right? So basically the current state to output this correspondence. So if you look at the middle columns, right? So that's where we try to compute the next states, right? First, for next state, we actually need to look at both the current state and the input, right? So in this case, somehow my pointer's gone. So in this case, if you look at this specific entry, right? So this entry is where we are at. The current state is at init, right? And input. So let me remove this one. And the input is in 0, right? Input is 0. So this means that at current state init, if input is 0, we're going to be staying at init state. Okay, so hopefully this is intuitive enough, right? Very straightforward. Okay, so but this is not quite the true stable, right? No, we do have some 0 1s over here. But if you look at other entries, right? So those are not binary yet. No, we are still using the English names, right, of those states. Although the English alphabet is kind of digital, right? We already talked about that. But this is not the kind of digital system that we like the most, right? We like everything to be 0 1. So what do we do? Any suggestions? So how do we convert this truth table, right? This is a more descriptive version. This is a fairly descriptive truth table. Right, later on when you guys work on homework, exam, you can actually start with this, right? Before you make mistake, right? So do something, more readable first. Right, so yes, so we need to actually convert this English, right? This labels, right, in English into 0 1s. So how do we go about that? Right, so yeah, many of you are already saying you already mentioned the correct solution. So basically, we can just come up with a binary encoding, right? So since we have 4 states, we actually need 2 bits, right? We need at least 2 bits. So let's just assign 0 0 over here. So see here, I'm putting the 0 0 in the square brackets, right? This does not mean output. This means the encoding, the binary encoding of the state. So we put 0 0, right, for init, and assign 0 1 over here, right, for GAL1, 1 0 1 1, right? Okay, so this is one way to assign things. Once we are done with this, then we can just replace the labels, right, with this binary code, and we are done. So we have the complete truth table. All right, so one thing I actually want to make a note is, if you look at this encoding, right, this is actually just one way to encode, right? There are actually many different ways to encode. It's actually totally okay to assign 1 1 to init, right, and 1 0 to GAL1, right? We can totally just reverse it. That's also a legal encoding, right? We can also, spend 3 bits or even 4 bits. Okay, we can say like init is 0 0 0 1. We can do something called 1 hot encoding, and this one is 0 0 1 0, and this one is 0 1 0 0, and this one is 1 0 0 0. Okay. There are actually many different ways to come up with a binary encoding for these states in the finite machine. But in our class, right, so we just go with the most intuitive one, most natural one, right? So where we use the fewest bits, right? And we just follow the order of the states and then assign a binary value for each state. And in the actual CAD tool, like Quartus, the CAD tool is actually smart enough to come up with the right kind of encoding that try to minimize the circuits. Okay, so the encoding that we have over here may not give us the smallest circuit. Okay? There's something to, something useful to know. All right, so now that we have this truth table, right, we can actually derive the circuit. So let's start with output. How about that? What is out? Can you guys just give me the expression? We just need to look at this a single one, right? We don't really need to draw a kernel map, right? In this case, right? Very good. S1, S0, right? That's it. Okay. Right. Again, these are the current state values, right? In this truth table, the current states are also part of the inputs, right? So what else? We also want to come up with the circuit, right? For this next state, right? We want to come with the next state logic. Let's just do one, right? In the next state, we also have two bits, right? S1 star and S0 star. Let's just focus on S0 star, right over here. So we have 3 ones, right? Okay, maybe we can just draw a kernel map. Just want to remind you guys, right? You guys have done plenty of kernel map, but since most likely I'll ask you about kernel map, right? In the first frame, let's just do one. Okay. All right. Okay. 0, 0, or 0, 1, 1, 1, 1, 0. So where are the ones? This one, right? 0, 0, 1 over here, right? Okay. Let me know if I did anything wrong. Right? And this one, right? So this one is 1. So I'm reading S1, S0, and in, right? 1, 0, 1. 1, 0, 1 is here, right? And this one is 1, 1, 1 here. Okay. So this is the kernel map, right? The rest are zeros. So how many prime implicants do we have? 2, right? 2 circles, basically. Okay, first, start with the corners. Right? Focus on corners. What is this? What is this circle? Can you tell me? This is for Alma's asking, what is the current? This is for S0 star. Okay. We are trying to derive the circuit for S0 star. Right, very good. So this is okay. How about what else? This one, right? This circle. What is this? S1, right? In and the atom, right? Okay. Any questions? Alma, is it clear? Okay, you guys can do the same thing for S1 star, right? So just follow the same routine, right? Very similar to conventional logic. All right, so this is more. Right? Let's also look at melee. So with melee, the input table, input, right? So we have the same set of inputs, right? But we have to be careful with the output, right? So table, the optimization of the table will look slightly different. So this is where we actually need to push, right, out into this sort of middle columns, right? And we use a comma, right, to separate S star and out. The way to read this table is, okay, so we look at the current state, right? Current state, and let's say init, right? If input is 1, we are going to go to got 1 state, right? So this is next state, and we also output 0, right? We use a comma to separate the next state, right? And the output. That's how we read this state, this truth table for Mini diagram. Any questions? No? Okay, all right, very good. So again, over here, we are using the labels first, right? So we first fill in the labels of the states. And we can quickly come up with the binary encoding again, right, for each state, and then replace the labels with this 0 ones, right? So for each state. So let's try to derive the logic again for out. What is out? What's that? Anyone? Maybe let's just look at this. More space. What is out? Okay. So we have a single one here, right? Okay. If you just read out the min term, so what is this? This is S1, S0, right? And in, right? So, but Emily is saying that it's actually simpler, right? It's S1, S0 prime. What do we miss here? And some of you are saying, like, Ambrose, Mitchell, Lauren, they're saying that you're agreeing mostly with me, right? Okay. Do you guys agree that this is the right term? Yes or no? Yes? Okay. So first, okay, take a look at the truth table, right? Is this a complete truth table? If you look at input combinations for S1, S0, no. What's missing? We are encoding 3 states, right? And we're missing 1, 1 because we don't need that, right? We only have 3 states. So 1, 1, that's why the 1, 1 row is missing, right? What does that mean? Okay, very good. Right, some are saying the right answer, right? Don't care, say. So we are actually missing something like this, right? Okay, so given this don't care, do you guys think that we can further simplify? We can just draw this, right? So again, to help you guys, right, practice, right, a bit more about kernel map. We are talking about out, right? We want to do out. We have S1 at 0, right, in, right? Another kernel map. So we had the 1 here, so that was 1, 0, 1, right? 1, 0, 1 is here. We also have don't care here, right? So we have 2 don't cares here, right? So 1, 0, 0. You know, where's 1, 0, 0? So you guys are already seeing the quiz. Don't care here, right? And then don't care 1, 0, 1. So where's 1, 0? Oh, sorry. I think I read wrong. So it should be 1, 1, 0. 1, 1, 0. Don't care here. And then 1, 1, 1, right? Don't care here. Okay, so looks like we can actually further simplify, right? So this is basically S1. Yep. All right, any questions about these tables and how we minimize the circuit before we do the quiz? Okay, if not, let's just do the quiz.